Hey everyone, good afternoon. We have 15 minutes, so rather than going deep and covering everything that we've done with Ray, we thought we'd pick one use case and show what we've done. So we'll cover something called the many model framework. It leverages a lot of the Ray offerings that you all are already familiar with. So we're trying to show you how we've brought a particular use case, leveraging the efficiencies of Ray and how it ties into enterprise use cases and what we see in Snowflake. So just a safe harbor slide. If I make any commitments, disregard them. Don't hold me to that. So wanted to start with a forecasting use case. So many of you are familiar. Forecasting has become a lot more complex today. If you look at a retailer, for instance, if you're trying to forecast sales or you're trying to forecast inventory, it's not just simple linear data. You've got multimodal data. You have product feedback, which can be images, visuals, social media mentions, and so on. That complicates one part of it. And then when you're looking at forecasting over a time window, it's almost always non-linear. You have seasonality. You have seasons within seasons. Say you have a long weekend. You have a sporting event, right? All of these things can influence how forecasting happens. And then you also have external factors. You've got external market disruptions, geopolitical influences. So all of this makes it a complex problem that is best solved through transformers, and that's where in Snowflake, most of our customers end up using complex transformers for forecasting. So why is this relevant now? Why is this relevant in the context of Ray? This is why. In most retailers, and even look at, let's say, a pension fund trying to predict, like, I don't know, one of the stocks, how it's going to perform. You have to do this at a really granular level. And in the case of retailers, it has to be hyper-local. You want to predict a product per store, per geography, and using these transformers for each of them. So imagine now I have tens and thousands of these SKUs and products that you want to be able to forecast in this complex manner. Trying to orchestrate these tens of thousands of models to be trained concurrently, and remember, you want to do this almost many times daily, right? Because the dynamics keep changing. So training tens and thousands of these transformers on a daily basis, dealing with fault tolerance, dealing with retries, dealing with observability, dealing with cluster sizes and dynamic scaling, all of this becomes a really difficult distributed system problem. That's where Ray has been phenomenal, and we'll go into a little bit more detail on how Ray has been beneficial here, but that is effectively the problem. What we did was, to a user, to a developer who's trying to build such models, let's abstract away all of the complexities of the orchestration that we described. So as a user, what you want to do, make sure your data is partitioned. So you have your tables, it's a partition key that is either a SKU or a product ID or a store ID or whatever that is. That's one part of it. Develop your training function, so whatever transformer code you're writing, make sure that is a training function, and that's effectively all you need. Point Snowflake's APIs to, here is my training data set, here is the partition key, here is the training function, and I'll sit back, make sure you train all these models, make sure it's fault tolerant, and that's what we are handling for users. But it doesn't just end there, because you train the models and they still have to be used at the end of the day. You still have to operationalize it, deploy it. So what we also facilitate as part of this whole orchestration is to coalesce all these models into one referenceable asset artifact in the registry, from which you can still use the same partitioning patterns to then apply the forecasting on each one of these SKUs, each one of these product IDs. So all of this is made really seamless and efficient with this many model framework. And of course, there's a demo that kind of walks through some of that. So what powers all of this? So we have something called a container runtime. It is effectively a managed service that is built over Ray. You see where Ray plays a significant component there. What we've done is we've taken open source Ray, leveraged it as part of the Snowflake stack. So where we've made a lot of efficiencies is how you bring Snowflake data, which can be terabytes, petabytes, like you know, efficiently into a distributed cluster where data can optimally get fed directly into Ray actors, for instance. If you want to run other distributed processing like training and hyperparameter tuning, there's a lot of other simplifications and operational efficiencies that we bring in. So anyway, the point of the slide is the you open a notebook or you run a job, you get this entire operational environment for you where Ray is brought up for every such instance, and you get all of the Snowflake benefits, ease of use over that. So I'll leave you with that. This slide kind of digs a little bit into what we've done to actually implement this partitioned training and partitioned inference. And I'll hand this off to Shulin, who's the engineer for this project, and can talk you through some of that and do a demo.
All right. Thanks, Vinay. Hi, everyone. So moving on, we're going to show you like a quick dive into the overall architecture of how we actually chain many models in parallel across different partitions of data. So looking at the right-hand side of the diagram, from the top to the bottom, first we assume user provides us one or multiple Snowflake tables, given the partition columns for us to partition the data on. The framework itself will then take care of partition that tables into multiple partitions. And then when the partition is ready, it's going to be sent to the queue. So one key design here is actually we don't necessarily wait for all of the partitions to be ready before we actually start chaining on the each of the partitions. So this is making sure that our compute is as saturated as possible. So the ingestion part actually involves two parts to it. So first, we actually leverage Snowflake Warehouse to load the data from Snowflake to Snowflake Stage, which is essentially backed by AWS S3. As the Arrow IPC files. And then we leverage rate data, and we implemented our custom rate data source to actually download those Arrow IPC files from S3 in parallel through many different rate tasks to efficiently download them into every single rate actors. So once Arrow IPC file for a specific partition is ready, we push it to the queue. So we have a background thread basically keeps monitoring that queue, and whenever it detects there's a new partition ready, it's going to submit that reference to that Arrow IPC file along with the partition ID to the actor pool. So actor pool will then designate a specific actor to basically use our red data source to download those Arrow IPC files with red tests in parallel, and then start doing the chaining that user specified. One other main feature worth pointing out here is a lot of times, a lot of this many model chaining is actually runs very long, and user might not necessarily know how many nodes or resources you need to specify upfront. So we actually allows users to scale up or down while the workload is still running. So say in a situation where you realize that you don't have enough GPU nodes to really speed up your chaining, and you decided to add more to it, you can do that by scale up your cluster without interrupting the existing workflow. And we will have actually we call it actor pool scaler to detect that there is a new nodes joining, and then as a result of that, we'll actually create new actors that can actually pull down things from the queue to really speed up things. So without further ado, let me quickly show a live demo. We have 6 minutes left, so I need to speed up a little bit here. So here, this is the Snowflake notebook that is actually running, you can see, in the Snowflake CPU machine, currently is running on a single node with a CPU medium with 6 CPUs on it. So this demo, we're going to show you a synthetic data set. How do you run many model training run to actually predict the sales over a bunch of stores. So and then we're going to show you while it's running, what kind of observability you can get. And then after that, we train all those models. We can run a quick inference on them. So on the setup side, we create a session object to get access to the Snowflake data. We also create a stage, which is used to persist a bunch of many model training run artifacts. Then we show you how the data looks like. So here we have a bunch of store ID, product ID, and the dates and the sales for that date based on the price and competition pricing. And here we basically write a helper function that to prepare a 14 days of slicing a window. So basically, we're using the previous 14 days of features to predict the next day's sales. And this is just to massaging the data into that format. So moving into the meaty part here, So first of all, we define a very simple like PyTorch model. This is just for demo purposes. Then we define a chaining function. The chaining function here takes in two arguments. The first is the data connector. This data connector is only associated with one specific partition of data. And the second object is a context object that is provides some util information. For example, which partition ID this data connector is associated with. So you can see in the chaining function, I purposely throw an error when the chaining function is processing partition ID 5. I'll show in a bit in how this error actually gets surfaced to a user, or any other like error will be surfaced to the user in just a bit. So moving on, we prepare the data and we load it to a PyTorch data loader. We chain with a few epochs. And along the way, we print out some chaining loss. And then at the end, we return a model. So that's as simple as any user chaining function that could be. So after that, remember we start out our cluster with one single node. But here we can actually run our cell to scale it up to 2 nodes. Here, one key important thing is the scale cluster code here is asynchronous. So while our compute is working on pulling Docker image, starting up container, we can already start up doing our many model chaining. And so that whenever a new node is joining, it will automatically join our RAID cluster, and then we'll actually create a new actor for it to pick up new workloads. So here, ingestion and chaining are separate. So we see we chain on 10 stores, and ingestion finish up relatively quickly. So once ingestion finished, it added a queue, and then chaining is actually starting and running. And then you will see it increments at a period of 2, most likely because we have 2 nodes up and running at the same time, right? And while this is running, you can see there's a very nice live progress, as well as the resource usage for both of our nodes. And for more advanced users who want to see more like, who are more like experiments with array, we actually shows you array dashboard associated with this running notebook, right? This is a native array dashboard. You can see the nodes, you can see all the jobs and running, all the actors, etc. that we spin up, and to do more deep dive investigation. So let's just wait for one last run to finish. So if it failed, and this is kind of as expected. So if we call the get progress, you'll see out of 10 model runs, there's 1 failing and 9 succeeded. For the successful one, you can see we print out actually the chaining loss as expected. That's what we do in our chaining function. And I also show you how you can easily get a model. And let's move on to the fail one. This is more interesting. Remember, we purposely throw a potential error for partition ID 5, and user can easily filter out all of the failed partition and show the exact failure on that. And later on, say if they want to rechain or remodel only on the failed partitions, they can specify the partition ID for those failed partition ones and only start up a many model chaining run on those failed ones, so to save time and cost. Okay, so to save time, I already run this model registration before the session. So the TLDR here is once you chain these many models, you can easily log them to the model registry. And what it shows up is in the Snowflake model registry, you can see how the model input and output looks like, all the metadata, as well as all the model artifacts associated with this. So here we have 10 stores, each is a PyTorch model, and you can download them or do anything you want with it. So that's the main takeaway. And very quickly, on the inference part, we can create like a inference data set and pass it to our model object. And here we specify the data source as well as the partition ID. And we take care of routing each row to the correct submodel based on the store ID here. So we make sure that it does the right inference on the right model. And here, this is what an example like sample output looks like. So this is what it means is actually for a given store ID and product ID given on the past 14 days of data, this is what it predicts sales for the next day. And that's pretty much it for the demo. On a quick note on the performance, what we realize is that even for a single node situation, when we compare many model chaining to a serial run, as the partition size increases, we do see performance gains better. And this is mostly thanks to the pipeline parallelism of the data ingestion and chaining we've done. And furthermore, as we scale up the number of nodes from single node to multiple nodes, the performance also scales linearly as well. Basically, you can see from the green lines here is almost twice as low as the single node here. So that's pretty much it. So if you're interested, try it out. Feel free to scan the QR code here. This should take you to the notebook, and or any questions you have, we can take it offline. Thanks so much.